16th of May, 1943. The Ruhr Valley, Germany. It is 20 minutes past midnight, and the moon sits low and silver over the black water of the Möhne Reservoir. For years, this dam has held back 50 million tons of water, a vast grey wall of masonry rising 19 meters above the valley floor, its curved face so wide that a man standing at one end could barely see the other. It has survived bombing raids. It has survived the war. The Germans considered it invulnerable. Then the first Lancaster appears. It comes in low, impossibly low, barely 18 meters above the surface of the reservoir, its 4 Merlin engines hammering the night air with a sound like approaching thunder. The crew inside know exactly what they are doing and exactly how little margin for error they have. The pilot holds the aircraft steady at precisely 354 kilometers per hour. His hands do not shake. In the bomb bay, a weapon unlike anything ever built begins to spin. It reaches 500 revolutions per minute, then the bomb aimer releases it. What drops is not a bomb in any conventional sense. It is a cylinder, roughly the size and shape of a garden roller, black and squat, weighing nearly 4.5 tons. But instead of falling, it bounces. It skips across the surface of the reservoir like a stone thrown by a schoolboy, each contact throwing up a curtain of white spray, each bounce slightly shorter than the last, until the spinning, rolling shape reaches the face of the dam, disappears beneath the surface, sinks and detonates. The explosion, when it comes, is felt across the valley. This is Operation Chastise. This is the night that a group of engineers, scientists, and airmen used a weapon so improbable, so violently innovative, that it flooded German valleys, destroyed critical infrastructure, and shocked the world. This is the story of the bouncing bomb, and of the extraordinary mind who made it possible. To understand why the bouncing bomb was invented, you first need to understand the problem that no one else had managed to solve. By 1940, the strategic importance of the Ruhr Valley to the German war machine was beyond question. The region produced roughly a third of Germany's total steel output, and that steel production depended entirely on water, enormous quantities of it drawn from a series of massive reservoirs held back by some of the most formidable dams in Europe. The Möhne alone stored approximately 130 million cubic meters of water. The Ada held more. Together, they were the lifeblood of German heavy industry. British planners had known for years that destroying these dams could cripple German production. As early as 1937, Air Ministry studies identified the Möhne as a priority target. The mathematics were compelling. Breach the dam, and you not only flood the valleys downstream, destroying roads, railways, and factories, but you simultaneously deprive the entire Ruhr industrial complex of the water it needed to function. You did not need to bomb individual factories. You bombed the thing that everything else depended on. The problem was that it was essentially impossible. Conventional bombing of a dam face was almost useless. A standard high-explosive bomb striking the crest or the upstream face would crater the masonry. Certainly, but the sheer mass of a structure like the Möhne, over 30 meters thick at its base, simply absorbed the impact. Calculations suggested you would need a bomb of at least 30,000 pounds to breach a dam by direct conventional attack, and no aircraft in 1940, or for several years afterward, could carry anything approaching that weight. Even if you could deliver such a weapon, hitting a specific point on a narrow dam crest from altitude, in darkness, under anti-aircraft fire, was a feat that defied probability. Torpedo attacks were equally hopeless. The Germans had anticipated this threat and strung torpedo nets across the face of their major reservoirs. Any conventional underwater weapon would be stopped well short of the dam wall. The Möhne had nets extending 5 meters below the surface and stretching the full width of the reservoir. They had been installed specifically to defeat the approach of underwater ordnance. It seemed, to most planners, that the dams were simply safe. Barnes Wallis did not agree. Wallace was already one of Britain's most respected engineers by the time he turned his attention to the dam problem. Born in Ripley, Derbyshire, in 1887, he had spent decades working for Vickers Aviation, where he had pioneered the geodesic construction method used in the Wellington bomber, a revolutionary approach that gave the aircraft exceptional structural strength at relatively low weight. He was methodical, brilliant, and possessed of a particular quality that defined his approach to engineering. He did not accept that existing constraints were permanent. Working initially from his home at White Hill House in Effingham, Surrey, and later at the Vickers Research Facility at Weybridge, Wallace began calculating in late 1941 and through 1942. He started not with the bomb itself, but with the dam. He wanted to understand precisely how much force, applied precisely where, would be needed to cause a catastrophic breach. His calculations, refined over months, led him to a startling conclusion. You did not need a massive bomb hitting the top of the dam. You needed a much smaller charge placed directly against the upstream face, as deep as possible, as close as possible to the foundations. The water itself would do the rest. A detonation at depth pressed directly against the dam wall would create a shock wave that the surrounding water would transmit and amplify rather than dissipate. The physics involved are related to the concept of a water hammer, the same effect that causes pipes to clank when you shut a tap quickly, but operating at a scale and intensity that would subject the masonry to stresses it could not withstand. Wallace calculated that a charge of approximately 6,600 pounds of Torpex explosive, detonated at a depth of around 9 meters and in direct contact with the dam face, would breach the Myrna. The weapon that would deliver that charge was what he called Upkeep. Upkeep was a cylindrical mine, 1.27 meters in diameter and 1.52 meters long. The production version weighed approximately 4,196 kilograms, roughly the weight of a small lorry. Its casing was made of steel plate, and it contained a charge of Torpex explosive fused with both hydrostatic pistols, which would trigger at a specified depth, and a self-destruct mechanism set to detonate after 90 seconds to prevent capture or recovery of an unexploded weapon. The spinning mechanism was the crucial innovation. By mounting the cylinder on rotating bearings inside the Lancaster's modified bomb bay and driving it backwards against the direction of flight, at 500 revolutions per minute using a hydraulic motor, Wallace imparted a backspin that performed two essential functions simultaneously. First, it gave the weapon the gyroscopic stability to skip reliably across water rather than tumbling on impact. Second, when the spinning cylinder finally reached the dam face and was driven down the vertical masonry by its own forward momentum, the backspin caused it to hug the wall as it sank, ensuring the explosion occurred at depth with the charge in direct contact with the stone, removing the torpedo nets from the equation entirely. To achieve the necessary skip trajectory, the aircraft had to release Upkeep from a precise altitude of exactly 60 feet, roughly 18 meters, while flying at exactly 354 kilometers per hour. The bomb had to be released at a precise distance from the dam face, approximately 425 meters, to ensure it arrived spinning at the correct speed and angle. Getting these parameters wrong by even a small margin meant the weapon either broke up on impact, skipped clean over the dam, or detonated too far from the face to be effective. The manufacturing of Upkeep was carried out in conditions of intense secrecy. The casings were produced at several different engineering firms across Britain to obscure the weapon's true purpose, with no single contractor aware of the complete assembly. Final preparation and the loading of explosive charges was handled under close supervision at RAF Scampton in Lincolnshire, where 617 Squadron had been formed specifically for this operation in March 1943. 617 Squadron, under Wing Commander Guy Gibson, comprised some of the most experienced aircrew in Bomber Command. They had been given only 2 months to train for an operation whose nature they were not initially told. They practiced flying at extremely low altitudes over reservoirs across Britain and Wales, including Derwent Water in Derbyshire and the Ibrook Reservoir in Rutland, learning to hold the aircraft steady at 60 feet in darkness using spotlights mounted beneath the aircraft. Two beams angled to converge precisely at the correct altitude, creating a visual reference point on the water's surface. If you are finding this interesting, a quick subscribe helps more than you know. At 33 minutes past midnight on the 17th of May, 1943, 3 Upkeep weapons were dropped against the Möhne Dam in succession. The third detonation breached the wall. Water began to pour through a gap that rapidly widened to over 70 meters as the structure gave way, releasing a wave estimated at 10 meters high into the valley below. Within hours, the Eder Dam had also been breached, releasing a further 202 million cubic meters of water. The operational consequences were severe and immediate. The flood wave from the Möhne destroyed or heavily damaged roads, bridges, and railway lines across a front of roughly 80 kilometers. Power stations serving the Ruhr were flooded. Agricultural land was inundated. The water supply infrastructure on which German industrial production depended was severely disrupted. German documents captured after the war confirmed that production in several Ruhr industries was reduced for weeks and, in some cases, months. The human cost was devastating on both sides. The floods killed an estimated 1,600 civilians in the valleys downstream, a figure that included a significant number of forced laborers from occupied countries who had been housed in camps near the rivers. 8 of the 19 Lancaster aircraft dispatched on Operation Chastise were lost, and 53 air crew were killed, a casualty rate of over 50% among the attacking force. The operation was a tactical success paid for in blood. The Germans moved quickly to repair the dams, mobilizing thousands of workers in a massive reconstruction effort that had the Möhne operational again by the following September. Too quickly for the RAF to conduct follow-up attacks before the next winter's water levels made the reservoirs useful again. This outcome would later form the basis of much historical debate about the raid's long-term strategic impact, debate that continues to the present day. What the Germans attempted to build in response to Upkeep was notable for what it revealed about how well they understood what had been done to them. German engineering teams analyzed the breach patterns and concluded, correctly, that a spinning cylindrical mine had been used. They undertook research into similar weapons, and some records suggest partial development of a German equivalent, though no operational German bouncing bomb was ever deployed. The Americans, who had been briefed on Upkeep through Allied intelligence channels, also conducted trials of cylindrical skipping bombs in 1944, though again none reached operational status. The Canadians and Australians who served in 617 Squadron during and after Operation Chastise contributed significantly to the dissemination of the technical knowledge involved in the tactical concept of precision low-level attack on specific infrastructure targets shaped how 617 Squadron continued to operate throughout the war, later using the massive Tallboy and Grand Slam earthquake bombs, also designed by Wallace, to devastating effect against the Tirpitz, the Bielefeld Viaduct, and numerous other hardened targets. By comparison, the Americans' own solutions to the problem of attacking hardened targets tended toward the brute force of high-altitude precision bombing, refined by the development of the Norden bomb sight. Effective in certain conditions, but unable to achieve the intimate, contact-charge detonation that Wallace had calculated was necessary. No American weapon of the period matched Upkeep's specific combination of delivery method and explosive placement. The British had approached the problem differently, not by building a bigger bomb, but by finding a smarter way to put a medium-sized one exactly where it needed to be. Wallace himself remained deeply troubled by the loss of the 53 men who had not returned from Operation Chastise. He attended no celebratory functions after the raid and reportedly broke down when told the casualty figures. He continued to work for decades more, His later innovations included variable geometry wing designs that anticipated the swing-wing aircraft of the 1960s and 1970s. But by his own account, the memory of Chastise stayed with him always. The debate over the dam raid's actual strategic impact is one that historians have engaged with at length and without final resolution. On one side, there are those who argue that the disruption to German industry was temporary, that the dams were repaired faster than anticipated, and that the 53 deaths among 617 Squadron's air crew represented too high a price for what was achieved in material terms. This is a serious argument, made by serious historians, and it deserves to be taken seriously. On the other side, there is the argument that the psychological impact of the raid extended far beyond the immediate material damage, that the breach of the supposedly invulnerable Möhne Dam demonstrated to both German civilians and German military planners that nowhere in the Reich was beyond reach, that no piece of infrastructure, however large and however defended, could be considered safe. This argument, too, has weight. What is not in dispute is the technical achievement itself. Wallace had identified a problem, analyzed it from first principles, and designed a solution so precisely calibrated to the specific conditions of the target that it worked exactly as calculated on the first operational use. The bouncing bomb was not a lucky improvisation. It was the product of 2 years of rigorous mathematical work, model testing in water tanks at the National Physical Laboratory, and practical trials conducted over Chesil Beach in Dorset and later over Reculver in Kent. A full-scale Avro Lancaster, modified to carry Upkeep and designated the Lancaster Type 464 provisioning, can be seen today at the Royal Air Force Museum in Hendon, North London. Several Upkeep casings, inert, their explosive charges long removed, survive in museum collections across Britain. At the Derwent Reservoir in Derbyshire, where 617 Squadron practiced their runs in the month before the raid, a small memorial stands at the water's edge. So return for a moment to that reservoir in the Ruhr Valley, in the minutes after midnight on 16th May, 1943. The moon is still above the water. The aircraft is still coming in low, impossibly low, its engines shaking the air. In the bomb bay, something unprecedented is spinning backwards at 500 revolutions per minute, waiting for the precise moment, the precise altitude, the precise speed. The bomb falls, it bounces, it sinks, it detonates. 50 million tons of water begin to move. Barnes Wallis solved a problem that everyone else had agreed was impossible. He did it by ignoring the constraints that had stopped everyone else and working backwards from the physics, from the dam, to the explosion, to the delivery, to the aircraft, to the spinning. Every element served every other element. There was no wasted ingenuity and no room for error. The Möhne Dam had stood for 30 years. It stood for 33 minutes against the weapon that Wallace built. That is what happens when someone who genuinely understands a problem refuses to accept that it cannot be solved. You do not always need a bigger weapon. Sometimes you need a better one, and sometimes you need a man working alone at a drawing board in Surrey in the middle of a war who is willing to think about dropping a spinning cylinder 18 meters above a lake in the dark and sending the whole thing bouncing toward a wall of stone and water that the enemy believed was safe forever. He was right. They were wrong. The water proved it. If you liked my video, please share your opinion in the comments box and subscribe to the channel. Also, turn on the bell icon so that the latest videos like this keep reaching you. See you in the next video. Take care and goodbye.